Okay, guys, so the next example, let's say y prime equals 1 over x with y of 0 equals 0. So this equation, do you think it satisfies the conditions of Picard theorem or not? So this equation does not satisfy the conditions of Picard's theorem. What is f of x and y here? Here f of x and y is equal to 1 over x. And this is discontinuous at 0 and 0. Let me say at x and y equals 0 and 0. See, there is a point given to us as an initial condition called x0 and y0. Here, x0 and y0, both of them are 0 because the initial condition is of the form y of x0 equals y0. Here it says y of 0 equals 0, so x0, y0, they're both 0. So we need to check continuity of f at the point x0, y0, which is 0 and 0. But here 1 over x is not continuous at x equals 0. So we can say that f of x and y equals 1 over x is discontinuous at x and y equals 0, 0. Since 1 over x is not continuous at x equals 0. So even the first condition of Picard theorem does not hold. Previous example, the first condition hold, the function was continuous, but the partial derivative respect to y did not exist. But here, even the first condition does not hold. The function is discontinuous at the point x0, y0. And it can be shown that this equation has no solution. So this is, you can check this. This is no surprise that, you know, the conditions of the Picard theorem do not hold and the theorem and the equation does not have solution. So please note that if the conditions do not hold, you cannot automatically say that there is no solution or the solution is not unique. Because if the conditions of the theorem do not hold, it just simply means we cannot or we are not allowed to apply the theorem. But the equation may or may not have solution. And if it has, it may be unique or may not be unique. So the fact that the conditions do not hold, it just simply means that we are not allowed to apply the theorem for this example. That's all it means. So this is this equation with this initial condition. If I change the initial condition, then the Picard's theorem may become applicable. So for example, again, if you consider the same equation, this time with, let's say, a y of 1 equals 1, then you can check that Picard's theorem can be this time applied to conclude that this equation has a unique solution. So still same equation, but I change the initial condition. Now for this one, you can, because you have to check the continuity of f at x0, y0. I have changed x0, y0 here. This time the function becomes continuous and partial derivative of f respect to y also exists and is continuous at this point 1 and 1. And therefore you can check these two conditions, verify the details, and then conclude that Picard's theorem can be applied to conclude that the equation has a unique solution. Now, one remark I want to mention here is that Picard's theorem guarantees a unique solution under conditions mentioned above. Only locally, i.e., a unique solution exists on an open neighborhood an open interval containing x naught containing x naught on an open neighborhood of x naught. See, an open interval containing x naught. However, the solution may not be well defined on -infinity to infinity or r. So when we say that the solution exists, means a solution around the point, a little bit to the left and a little bit to the right of the point x naught must exist and must be unique. But it may not be defined on the whole real numbers or -infinity to infinity. So when we talked about Picard's theorem, when we talked about existence and uniqueness of the solution, the context was whether the solution exists or is unique around the given point x naught, a little bit to the left and a little bit to the right of the point. An open interval containing the point means an interval that contains x naught as a middle point, middle point. So a little bit to the left, a little bit to the right. It may not be symmetric, but x naught cannot be an end point of that interval. So x naught minus some number to x naught plus some number. The context is whether a solution exists on an interval of the form x naught minus some number to x naught plus some number. And Picard's theorem says that such a solution exists with the conditions of continuity that we discussed. But even if with the conditions of continuity, the solution that Picard's theorem guarantees may not be defined on the whole real numbers, on the whole -infinity to infinity. Let me give you an example. For example, consider y prime equals y squared with a y of 0 equals 1. This equation satisfies the conditions of Picard's theorem check. So a unique solution must exist also check that the solution of this equation can be written as y equals 1 over 1 minus x. So see, 1 over 1 minus x is not defined on the whole minus infinity to infinity. It's defined around 0, which is, as expected, defined on a neighborhood of x not equals 0, say on -1 to 1, for example, on -1 to 1, it's defined, but it's not defined, globally. On minus infinity to infinity. Obviously, the domain of this function is not all real numbers because x equals 1 is not in the domain. But around 0, a little bit to the left, a little bit to the right of 0, in this case, from -1 to 1, or you could say from -2 to 1, or -3 to 1, or -2 to, for example, 0.7, right? You can choose the interval yourself, but the point is a little bit to the left of 0 and a little bit to the right of 0. It is defined, for example, on an interval of the form -1 to 1, but it's not defined on the whole real numbers. So Picard's theorem only guarantees existence and uniqueness of solution locally for an interval, open interval containing x naught, a little bit to the left and a little bit to the right of x naught. All right, let's move on to the next topic, 1.3, separable equations. A separable equation, and let me say a first order, because you're talking about first order equations, right? So a first order separable ODE is an equation of the form y prime equals, let's say, f of x times g of y. So how to solve this equation? How to solve? So see, if you have an equation of the form y prime equals f of x times g of y, a function of x times a function of y, then it's called separable. And how can we solve this type of equation? Well, as you can guess from the name, you can separate x's and separate y's. So separate y's meaning that take all y's into one side and all x's into the other side, and then you can integrate both sides. But of course, when you want to take all y's into one side, you have to divide by some function here, in this case g of y. And as you can see from the previous examples, if you want to divide by a function, first you need to make sure that that function is non-zero. If it's 0, then you cannot divide, and you can take another approach, usually a simpler approach, to solve the equation. But if the function is non-zero, you have a guarantee that the function is non-zero, then you can divide both sides by g of y to separate y's into one side and separate x's into other side, and then integrate and solve. So let me show you how you can solve this equation, this type of equation. So let me consider two possibilities or two cases. Case 1, if g of y is equal to 0, find the roots of g of y. Say y equals y1 to y equals ym. Then the constant functions y equals y1 to y equals ym will be the solutions of the ODE above. Why? Because for these values, say verifying, let's say if we have y equals yi, let's say, then what will be the derivative? A constant function. What will be the derivative of this function? Derivative of a constant function is 0. Then dy to dx will be 0. And what about the other side? Remember, the equation that we want to solve is this equation, y prime equals f of x times g of y. So if y equals yi, the constant function yi, then the derivative is 0. Derivative of any constant function is 0. What about the right-hand side? And right-hand side will be g of f of x times g of y, which is 0 for y equals yi. Because for y equals yi, g of y is 0, and if g of y is 0, anything times 0 is 0. And therefore y prime will be equal to f of x times g of y. So if g of y is 0, then it's easy to solve. You just need to find the roots of g, and y equals those numbers as constant function will be the solutions for your differential equation. And case 2, if g of y is not 0, then divide both sides by g of y and integrate both sides. See, our equation is y prime, which is dy to dx, equals f of x times g of y. So if g of y is non-zero, I can divide both sides by g of y. Then I'll get dy over g of y equals f of x dx. And then I can integrate both sides. Integral dy over g of y equals integral f of x dx. And then you solve this. Now let's look at an example. Let's say y prime equals xy with y of 0 equals 0. Is this separable? This equation is separable with f of x equals x, g of y equals y. It's of the form f of x times g of y, and f of x here is x, g of y is y, x times y. Now we want to solve it. First, we need to see whether g of y, which is y in this case, is it 0 or not? Well, it could be 0 because y of 0 is 0. I cannot rule out y being 0. If y of 0 was 5, for example, or anything other than 0, I could say that y cannot be constant function 0 because constant function 0 is always 0. But y of 0, for example, is 5 or is 2. But y of 0 right now is 0. So we cannot say y is non-zero as a constant function. So we said that in that case, if g of y is 0, then the roots of this will be the solution. And roots of y is y equals 0 itself. So here, the root of g of y equals y will be the solution, which means that y equals 0. again, as a constant function. Y equals 0 as a constant function is the solution for this. If you want to verify, dy to dx is 0 and x times y is 0. So y prime equals xy. And y of 0 is 0 as well, because constant function 0 is always 0, and in particular at 0, it's 0. Okay, I think my screen was freezed. So let me show you the solution one more time. So I was solving this equation, and I was saying that this equation is separable with f of x equals x, g of y equals y. And we cannot say y is non-zero because y of 0 is 0. If y of 0 was something other than 0, we could say y is non-zero. And so we are in case 1. In case 1, the root of g will be the solution. Or if there are few of them, any of them could be potentially the solution. Let me say the root of g of y equals y that satisfy the initial condition. Because if g of y has more than one root, then you need to see, because if it has more than one root, let's say it has 5 roots, all those 5 roots will satisfy the equation, because there are two things, satisfying the equation and satisfying the initial condition. If g of y has 5 roots, all those 5 roots will satisfy the equation, but then you have to see among those 5 roots, which one satisfies the initial condition as well. But right now it's very simple because this g has only one root, which is 0, and that root also satisfies the initial condition, which is y of 0 equals 0. So the root of this is y equals 0. And this y equals 0, as we said, satisfies the equation because y prime is 0, derivative of constant function is 0, x times y is 0 because x, anything times 0 is 0. And it also satisfies the initial condition, y of 0 equals 0, because if you have a constant function 0, it will be always 0, and in particular at 0 will be 0 as well. So let's look at the next example. Y prime equals xy divided by y squared plus 1 with, let's say, y of 0 equals 2 this time. Okay, again, first of all, we have to note that this equation is a separable equation. So first, note that this equation is of the form y prime equals f of x times g of y with f of x equals x, g of y equals y over y squared plus 1. So it is separable. And to solve this equation, we have to see whether g of y is not 0. Well, g of y is y over y squared plus 1. It will be not 0 if y is not 0. And y is not 0 because y of 0 is 2. We can say that y is not 0 since y of 0 is 2, which is not 0. So g of y is not 0. Hence, we can divide. If it's not 0, we can divide by it. Divide both sides by g of y. Then what do we get? So see y prime, which is dy to dx. This is x times y over y squared plus 1. And then if we divide both sides by y over y squared plus 1, then we get dy. What do we get? We get dy times y squared plus 1 divided by y times dy, right? Because I'm dividing by y over y squared plus 1, which is equivalent with multiplying by y squared plus 1 over y. And then this is equal to x dx. And now I can integrate both sides. And then I'll get integral y plus 1 over y dy equals integral x dx. And then this is going to be y squared over 2 plus ln absolute value y equals x squared over 2 plus c. Remember, when you integrate both sides, we had this situation before. We don't have to include the constant c in both sides because c here represents an arbitrary constant. So if I include a plus c1 in the first integral and plus c2 in the second integral, well, I can just simply take one of the ci's to the other side. Let's say if I take c1 to the other side, then on the other side, I will have c2 minus c1, which I can call it c. I explained this before. So let me not repeat the details, but the point is, if you're integrating both sides, you don't have to include the arbitrary constant in both sides. One side is enough. Now we need to find this constant c. So to find this constant c, use the initial condition. Use the initial condition y of 0 equals 2. Y of 0 was 2. So see, that means our x0 is 0, our y0 is 2. Then I'll get 2 squared over 2 plus ln absolute value 2. Absolute value 2 is same as 2. So plus ln 2 equals 0 squared over 2 plus c. So that means c is equal to 4 over 2, 2 plus ln 2. C is 2 plus ln 2. So that means our final answer, the solution of the ODE or IVP, let me say it was an ODE coming with an initial condition. So overall, it's called IVP, initial value problem. The solution of IVP will be y squared over 2 y squared over 2 plus ln y, ln absolute value y equals x squared over 2 plus c is 2 plus ln 2, 2 plus ln 2. So note that our final answer is written using an implicit equation. So in Math 113, you learn the difference between an implicit equation and an explicit equation. Explicit equation is an equation which is of the form y equals a function of x. For example, y equals ln x, or y equals sine x times ln x, or cos x plus e to the x plus ln x, whatever. If you have y equals a function of x, that's called explicit equation. But implicit equation is an equation where it's the x and y are all mixed together, and I have different powers of y, or different expressions for y. It's not y equals something. As you can see here, it's y squared over 2 plus ln absolute value y equals a function of x. It's not just y equals a function of x. So this is called an implicit equation. Most implicit equations cannot be written as explicit equations. Some simple implicit equations can be written as explicit equation. If you solve for y, if you are successful in solving for y, you can write your implicit equation as an explicit equation. But if you are not able to solve for y, then implicit equation is just implicit equation. We have to leave it as an implicit equation. That's why in Math 113, implicit differentiation is very important topic, because for most implicit equations, we cannot write them as explicit equation. We have to have them as an implicit equation. That's why we need to have some tools for differentiating, even in those cases of implicit equation. So if you're not able to solve for y, if you have an implicit equation and you are not able to solve for y, that's okay. Just leave your equation in an implicit form. So this is an implicit equation that relates x and y implicitly. It's not explicit equation for y. It's not something of the form y equals a function of x. So it gives a relation between x and y implicitly. Okay, and now let's look at the next example. Let's say y prime equals 2x plus, let's say, sine xy. So is this a separable equation? This is not a separable equation because it's not of the form y prime equals f of x times g of y. Can verify this. Another example. Let's say y equals 2x plus 3y. Y prime equals 2x plus 3y. This is also not a separable equation. Again, you can verify this. Y prime equals 2x plus 3y is also not separable. You can verify this. If it was y prime equals 2x times 3y, it would have been separable, but y prime equals 2x plus 3y is not separable. Let's look at an application now. Application for separable equation. An application for separable equations. Basically, the application I want to talk about is Newton's law of cooling. We have discussed it before as well. I've mentioned it. But now let's look at it as an example of a separable equation. Newton's law of cooling. So as saw before, let's say if we put an object with, let's say, temperature T of T. This is temperature at time T in a room with temperature, with fixed temperature TE. E stands for environment. Then the rate of change, then according to Newton's law of cooling, according to Newton's law of cooling, the rate of change of T is proportional to the difference between object temperature and room temperature. If you remember, I gave a simple example before that. Imagine putting a putting a hot cup of coffee inside fridge versus putting a hot cup of coffee inside a very hot room. Of course, when you put a hot cup of coffee inside fridge, the temperature drops much faster compared to when you put it inside the hot room. And why is that? Because when you put inside the fridge, the difference between object temperature and environment temperature is much higher. So in general, we can say that the rate of change of object temperature is proportional to the difference between object temperature and room temperature. Mathematically, we can write this as, we can say that dt to dt is some constant k times Te minus T. So this is an example of a separable equation with here f of t is 1 and g of t is k times Te minus T. Or you can assume f of t is k, doesn't matter. You can say f of t is k and g of t is just Te minus T. So we said that in physics, instead of x and y, we have t and x. But in this case, we have t and t, small t as the independent variable, which is time, and capital T as the dependent variable, which is temperature. Now, dt to dt is, it should be f of t times g of capital T. Instead of f of x, g of y, here we have f of small t, g of capital T. F of small t, I can say is k, g of capital T, I can say is Te minus T. Or we can say f of small t is 1, g of capital T is k times Te minus T. Doesn't matter. In any case, we can say that this is a separable equation. Now, how do we solve this equation? Well, we have provided the recipe before. So let's look at an example of this case. So example. Example, Bob made a cup of coffee at t equals 0. In the beginning, the temperature was coffee temperature was 89 degrees Celsius. 1 minute later, coffee temperature was 85 degrees Celsius. Assume that room temperature is 22 degrees Celsius. At what time the coffee temperature will be 60 degrees Celsius? So we know that initially it's 89 degrees, 1 minute later, 85 degrees, room temperature is given. You want to know at what time it will be 60 degrees. It's going to be 2 minutes after the initial time, or 3 minutes, how long? So let's set up the equation. So by Newton's law of cooling, we can say that dt to dt is equal to some constant k times 22 minus t. See, it was k times te minus t. Te here is 22. So we can write the equation this way. Now, we can divide both sides by 22 minus t, but we have to make sure that it's non-zero. But why is it non-zero? We can divide both sides by 22 minus t. Why? Because 22 t, because t is not equal to 22. When we say t is not equal to 22, we mean it's not constant function 22. What we require here in order to be able to divide by this expression 22 minus t is that 22 minus t should not be constant function 0. If it's 0 at some point, that's okay. You know, if you have, for example, let's say equation 5 let's say if I have 5x equals 6 times 1 plus x, and let's say if you want to divide both sides by 1 plus x, that's okay. Although 1 plus x will be 0 at minus 1, but you're still allowed to divide by 1 plus x, because 1 plus x is not constant function 0. But then you can say, what about at minus 1? Well, at minus 1, so I can say that this is equivalent with this, except at minus 1. So I can make an exception that, you know, if x is minus 1, then this guy will be 0, then this equivalency will not be valid. If you see whether my screen is freezed. So this equivalency will be valid only if x is not minus 1. So my point is, if you're dividing by a function, as long as that function is not constant function 0, then that's okay. We are not allowed to divide by constant function 0. But if the function is 0 at some point, we can still divide by it. So what we require here is that 22 minus t must not be constant function 0, which means t must not be constant function 22. And that's of course true. T is not constant function 0 and constant function 22, since t of 0 at the beginning was 89 degrees, right? The beginning was 89 degrees. So cannot be constant function 22 because at some point was 89. So now if I divide both sides by 22 minus t, then I'll get the t over 22 minus t equals k, k times d small t. Now integrate both sides. If I integrate both sides, what do we get? Or before integrating, let me multiply both sides with minus 1. Then I'll get dt over t minus 22 equals minus k dt. And now integrate both sides. Then we get integral dt over t minus 22 equals minus k integral dt. And then this gives ln, absolute value t minus 22 equals minus kt plus c. Antiderivative of integral dt is t plus c. So it doesn't matter, you can say minus kt minus kc or just minus kt plus c, because c is an arbitrary constant, right? So even if it's minus kc, you can replace it by another constant like d. Doesn't matter. Because c is arbitrary constant, doesn't matter whether I say minus kc or I say just plus c. And then this means that absolute value t minus 22 equals e to power minus kt plus c. ln something is minus kt plus c, so that expression is e to this power. And e to this power, I can write it as e to power c times e to power minus kt. E to power c, I can call it d. So let's define d as e to power c. Then I'll have d times e to power minus kt. And then I'll get t minus 22 equals plus minus d e to power minus kt, right? Because absolute value t minus 22 was d e to power minus kt. Okay, absolute value t minus 22 was d e to power minus kt. So t minus 22 itself will be plus minus d e to power minus kt. Now again, similar to the examples we did before, this type, plus minus d, I can call it f. So let's give it a name, plus minus d. Let's give it a name, call it f. So then f, let's define f as plus minus d. Then I'll have f times e to power minus kt, where f is a positive or negative constant. Because d was positive, d was e to power c, so positive, and f is plus minus d, so f is a positive or negative constant. Positive or negative constant. And then we need to, of course, find f, but so first let me write t. So look at this equation. We have t minus 22 equals f times e to the power minus kt. So what will be t? So t of t will be 22 plus f e to the power minus kt. I just simply took 22 to the other side. It becomes 22 plus f e to the power minus kt. And now let's use the initial condition. Now we use the initial conditions. To find f and k above. So our first initial condition was t of 0 equals 89. So that gives 22 plus f e to power 0 equals 89. And that gives 22 plus f equals 89. This gives the value of f. F will be 67. F will be 67. So t of t, substitute back. T of t will be, remember we had t of t equals this expression. We already found f. So let's replace f with 67. Then t of t will be 22 plus 67 times e to power minus kt. And now let's find k. Now let's find k. And t of 1 equals 85, right? So that gives 22 plus 67 times e to power minus k equals 85. So that gives 67 times e to the power minus k equals 63. 85 minus 22. 85 minus 22 is 63. That gives e to the power minus k equals 63 over 67. Take ln from both sides. Then we get ln e to the power minus k equals ln 63 over 67. And ln e to the power minus k means minus k ln e, but ln e is 1. So this will be minus k equals ln 63 over 67. That gives k equals minus ln 63 over 67, which is same as ln 67 over 63. Minus ln 63 over 67 is the same as ln 67 over 63. You can use your calculator to estimate this value for ln 67 over 63. You will see it's almost equal to 0.0616. And then now that we have the value of t, we can say that t of t is equal to 22 plus 67 times e to the power minus k. K was 0.0616 down and t. Right, so see we had t of t, the equation for t of t, 22 plus f e to the power minus kt. We had two initial conditions. We use one of them to find f. We use the other one to find k. Once you have the value of f and k, we can substitute back, and we get this equation for t. And what is the last thing you want to do? Let's read the question one more time. It was asking us to find the time. At what time coffee temperature will be 60 degrees. We want to find the time, the small t value, for which capital T becomes 60. We know that capital T, which is the temperature of the coffee, we want that to be 60, and we want to find the value of small t. So we know that capital T is 60. But lastly, we need to find the value of t, small t, the time for which capital T of t is 60. So capital T of t is 60, which is supposed to be 22 plus 67 e to power minus 0.0616 t. And then this will give me 38 equals 60 minus 22, 38 equals 67 e to power minus 0.0616 t. And then if we take ln, divide by 67 first, and then take ln. And what do we get? So divide by 67, we get 38 over 67 e to power minus 0.0616 t. And take ln, ln 38 over 67 equals minus 0.0616 t. And finally, t will be equal to, just divide by this constant. I have, this is a constant, this is another constant times t. And I want to find t. So just divide by this constant, both sides. Divide both sides by this constant here. Sorry, this constant here. And we will find the value of t. So this constant equals another constant times t. If we divide both sides by this constant, I'll find the value of t. T will be equal to 1 over minus 0.0616 times ln 38 over 67. And just use your calculator. You will see that this is almost equal to 9.21 minutes. So when Bob prepared this cup of coffee. Initially, the coffee was at 89 degrees. After 1 minute, I think it was 85 degrees. After 1 minute was 85 degrees, and the room temperature was 22. And if he's wondering how much he needs to wait in order for his coffee to be 60 degrees, let's say if he wants to drink the coffee when it's 60 degrees, right? Because he can't drink it when it's too hot, or he doesn't want to drink it when it's too cold. Let's say his ideal temperature is 60 degrees. In that case, our calculation shows that he has to wait 9 minutes, 9.21 minutes. You can convert it to seconds as well. This is in minutes, 9.21 minutes. And you can see, you can convert it because 0.2 minutes, you can see how many seconds it is. And then 9 minutes and that many seconds, he has to wait from the time that he prepared the coffee in order for temperature to become 60 degrees, and then he can drink it. All right, the next section, let's start the next section, 1.4, linear equations and the integrating factor. So the goal here is to solve a differential equation, a first order ODE of the form y prime plus p of x times y equals, let's say, f of x. So we said that a linear ODE means an ODE where y and all derivatives of y have power 1. Now we want to focus on the first order ODEs right now, and we want to focus on linear first order ODE. So that means that power of y and power of y prime must be both 1. But regarding x, we are allowed to have any type of function, so we have no restriction in that regard. So that's why I wrote my equation in the form y prime plus p of x times y equals f of x. You could say that, generally we could have some function, let's say q of x here as well as the coefficient of y prime. But even if that's the case, we can divide both sides by q of x, right? And make this leading coefficient 1. So that's why without a loss of generality, I can assume that this leading coefficient is 1, because even if it's not 1, I can divide both sides by that function and make it 1, right? For example, let's say if you have x squared y prime plus 3xy equals, let's say, e to the x. If you divide both sides by x squared, then I'll get y prime plus 3 over xy equals e to the x over x squared, right? So even if you have something like this initially, after you divide both sides by this coefficient, you get something something of this form, which is what I wrote here. So for this reason, this can be considered as the general form of a linear first order ODE. General form of a linear first order ODE. Now we want to solve this equation. We want to find the solution, or all the solutions for this equation. If no initial condition is given, of course, we know that we have infinitely many solutions. We want to find all of them. And if we have one initial condition, then we will have one solution. But in any case, let's see how we can find the solution for this type of equation. So the idea here is that to solve this equation, we want to multiply both sides of this equation by a function called the integrating factor that makes the left hand side of this equation and make it a whole derivative. derivative of a whole function. So the idea is to multiply both sides of equation above by a function r of x called the integrating factor that makes the left-hand side a whole derivative. Whole derivative means derivative of a function, because right left-hand side is, well, it's derivative of y, derivative of y plus p of x times y, right? But I want these two terms together. I want these two terms together to be derivative of some other function. How can I achieve that? If I multiply both sides by r of x with the proper choice of r of x, of course, not any choice of r of x. If the proper choice of r of x, I can make this whole package, the addition of these two terms, as a derivative of some other function. So let's see how we can do that. So I am multiplying both sides by r of x. So r of x times y prime plus r of x times p of x times y equals r of x times f of x. And I want this one, the left-hand side, we want this to be a d to dx of let's say r of x times y. Why d to dx of r of x times y? I said I want this to be derivative of some other function. Why am I choosing that other function to be r of x times y? Well, because when you consider derivative of r of x times y, according to the product rule, you already have r of x times y prime appeared, which is already appeared here. We just need to adjust r of x in a way that this second term here matches with the second term appeared in the product rule for the expansion of this derivative. Okay, so note that, I can say note that d to dx of r of x times y, according to the product rule, can be written as r of x times y prime plus r prime of x times y. And now we can choose, but this already matches with this, right? So choose r of x such that r of x times p of x is equal to r prime of x. So how can we choose r now so that r prime is equal to r times p? Well, r prime, we know that it means dr to dx. So dr to dx is equal to r times p of x. And if I divide both sides by r, I'm assuming that r is non-zero. Not constant function 0. So then I'll have dr over r equals p of x dx. And then if we integrate both sides, then we'll have integral dr over r equals integral p of x dx. And that means ln r or ln, let's say absolute value r equals integral p of x dx. So absolute value r equals e to power integral p of x dx. So then r is equal to plus or minus e to power integral p of x dx. So basically we have two choices, e to power integral p of x dx and minus e to power integral p of x dx. So just for convenience, let's stick with the first choice. Convenience. Let's choose r of x equals e to power integral p of x dx. So basically this is integrating factor for our equation. Integrating factor for our linear ODE, which was y prime plus p of x times y equals f of x. And we'll continue this next time. Next time I'll explain about the details, about the steps, that how we can use this integrating factor that we found the formula for it this time. So far we know that we want to solve an equation of this type. We know that if we use this r of x as the integrating factor, left-hand side becomes derivative of a whole function. And next time I will write down the steps one by one, how to solve the equation, and I will also show you examples and applications for this type of ODE. Okay, guys, so thank you and see you next time.